Okay, back again with video 3 of your ionic bonding chapter. Hopefully you've gotten a lot of practice in making the formulas for your ionic compounds, because that is a huge part of your SOL and of chemistry in general. That's something that you're going to have to be able to do for the rest of the year. So if you're still lost on it, stop watching this video. Don't go farther. Go back. Look up practice problems. Ask me for practice problems. Look at Khan Academy. Do anything you need to do to get it down pat. Okay, so now I'm assuming you're back because you've got it. Today, what we are going to talk about is a fancy word called nomenclature. All that means is, how do you name these compounds? Okay, when you look at something like NaCl, Ki, Cu3, PO4, okay, how do you actually say that? Because nobody walks around and says, oh yeah, CO3, PO4, We don't do that. Okay, there is a specific set of rules to name them. And believe it or not, it's easy. Okay, so if you are given the formula and you have to come up with a name, the cation always comes first. In fact, this is true when you're writing them as well. Okay, positive always comes before the negative. That's good life advice. You got to go home and tell your parents about something. Mom, I got an A in chemistry and I failed my Spanish test. You never put the failed Spanish test first, ever. You always give the good news and then the bad news. So, when you're naming the cation in chemistry, it is going to be the same name as the metal. You're not changing it. You're not adding anything to it. It stays exactly the same. Now, if it is a transition metal, okay, whenever you have those transition metals, remember they've got different charges. So make sure you add the Roman numeral. All right, that's a really important thing to remember. If you remember the last video, you'll remember that we talked about tin and lead being kind of special. So the special thing about tin and lead is they're not transition metals. They're right here, but they act like them. So if your cation in your ionic compound is any of these guys, or tin or lead, you need a Roman numeral. I will tell you that that is not always followed. Sometimes with things like silver, which can only be a +1, people leave out the Roman numeral. My advice for you guys, if it's in that D block, or if it's one of these two, you need to have a Roman numeral. Make your life simpler, okay? Even if it's only one possible charge, do it. Now, there are some complexities that can come with nomenclature, but we are sticking to binomials. That's ones that only have two things in them. But keep in mind, even something like Na3PO4 has only got two things. My cation is my sodium, and my phosphate is my anion. So remember your polyatomics. Okay, so back to the rules. The cation, you just name. Your anion, just like we did before, you're going to change the ending to IDE. Now, the only exception here are your polyatomics. I've always told you, you cannot mess with your polyatomic formulas. You don't get to change them. You don't get to do anything. Same is true with the name, okay? So, let's look at a couple examples, and you'll see some of these in your notes. NaCl, you guys already know the name of this. You know that this is sodium chloride. Well, now you know why. Okay, we're going to name the cation, that's sodium. Then we're going to name the anion and change the ending to IDE. That's what makes it sodium chloride. So, MgBr2 is the next example in your notes. I name my cation, magnesium. Then I name my anion, which is bromine, but I change the ending to IDE, magnesium bromide. Okay, when we have those polyatomics, okay, let's look at MgSO4. Name your cation, magnesium, and then name your anion. But because it's a polyatomic, we do not change the ending. So it's very simply magnesium sulfate. Okay, easy. Now, the only place your life gets a little tricky is with these transition metals. Okay, let's say we have FeCl2. Let's follow our rules. We're going to name it iron. Okay, and then my anion is chlorine, so I change it to chloride. The catch here is, I know it's a transition metal, so I know I need a Roman numeral. Well, which Roman numeral goes there? So the hard part here is you now have to figure out what Roman numeral goes there. So the way that I show people to do this, okay, is draw a line between your positive and your negative, between your anion and your cation. And you're sort of going to make a little chart, okay? This is the individual ion charge, okay? And then the next row, the top up here, is going to be the total charge based on your subscripts. For example, okay, we have to start with our negative every single time. Chlorine, if I go to my periodic table, has an ion charge of -1. But there are 2 chlorines here. So that gives me a total charge of -2. Well, if I need this entire compound to equal 0, which we've talked about before, I need the total charge over here to be a +2. Now, there's only one iron there, so that iron, okay, must have a charge of +2, making this iron 2 chloride. Okay? It's a little bit of work to figure it out. What a lot of people always try to do is take this subscript and just plink, make it the Roman numeral. That will work about 3/4 of the time, but the other 25% you'll end up wrong. Okay? I'll show you an example. If we look at FeO, okay, you might say, oh, I got this. This is iron 1 oxide because there's a 1 on the oxygen. And you would be wrong. Because if you look at the method I just showed you, FeO, okay, and then you don't have to write this chart out every time. You can kind of do it in your head or whatever. But if I look at the ion charge and I look at the total charge, okay, they start with my negative. If I look at my periodic table, my oxygen's a -2. There's only 1 oxygen, so the total is -2. I need it to equal 0, so this side has to be +2. That means this iron is iron 2. So don't just follow the subscripts. The other way that sometimes it gets confusing is when they both have subscripts. Okay, so again, I know it's iron something oxide. But if you go through this method, okay, Fe2O3, draw the line between my positive and negative, I'm looking for the ion charge and the total charge, and I always start with my negative. Oxygen, according to the periodic table, is a -2. There are 3 oxygens here, so that makes the total a -6. I need the whole thing to equal 0, so this side has to be a +6. But this time, I have 2 irons that are adding together to make that total of +6. The subscript times the ion charge is what gives me my total. So 2 times blank equals +6. My ion charge has to equal +3. Okay? So this is going to take, once again, some practice. But that's how you come up with the name. The only time it's hard is when you have transition metals. Going the other way is actually what you've already learned. Okay? Going from the name to the formula. So if I gave you, and this is the example in your notes, sodium sulfide, you actually already know how to do this. Okay? You're going to take sodium, which according to the periodic table is a +1. Sulfur, according to the periodic table, is a -2. I'm going to do my lovely little crisscross, Na2S1. There's my formula. Okay? So it's much easier going from the name, honestly, to the formula. If I give you iron 3 sulfide, we know iron 3, yes, I just wrote IR. Sorry about that. Okay, we know iron is a +3. We know sulfur's a -2. How did I know iron's a +3? That Roman numeral told me. So I draw my arrows, put my 2 down there, put my 3 down there, do my little circles, and there's my formula, Fe2S3. So the only way it gets complicated is once you have those Roman numerals and you're trying to go from the formula to the name. You just have to take your time and do it. Even though that's a separate day in class, I am going to go ahead and cover alloys today, just because it's the last little part of the PowerPoint and there's really not much to it. This isn't really an ionic bond. In fact, if we look at the summary, metal and nonmetal, that's a transfer of electrons, that's an ionic bond. Okay? Two nonmetals, or actually a nonmetal and hydrogen, are what we're going to learn next chapter. That's a covalent bond. But there's also the possibility of putting two metals together, and it's called a metallic bond. Now that is totally and completely misleading because the reality is they're not bonding. What they're really doing is they're really mixing together to make what we typically call an alloy. And it is a mixture. Okay, alloys are made by putting two metals together. You're usually melting them together and then cooling them down. And there's two ways this can happen. One way is called a substitutional alloy. Substitutional alloy. And a substitutional alloy is when the metals are roughly the same size. Okay, so I've got a great picture of it in your notes. I won't try to make it too, awesome here. But if I have these two things coming together, well, the pieces are all pretty much the same size. So what I'm going to get is they're going to kind of all be mixed in together. All right, so there's going to be a yellow one between these guys, and then a blue one and a blue one, and then the yellow one will be over here. They are literally substituting for each other in this grid, and I don't quite have enough room, so yes, the grid keeps going. This is what bronze is. Bronze is not actually an element. Bronze is an alloy. It's a mixture of copper and tin. Brass, okay, if you play a brass instrument, it's copper, it's tin, it's zinc. Gold, believe it or not, if you have gold jewelry, it is not pure gold. It is a mixture of gold and something else. A lot of people know gold is really, really soft. So they mix it with silver, they mix it with copper. Those are all substitutional alloys. The other kind of alloy is called an interstitial alloy. And that's what happens when one of the metals is much bigger than the other one. Okay, so again, I've got like a metal with pieces this size, and then I've got a metal with pieces this size. In this case, what I end up getting is the little ones just kind of fit between the big ones. Okay, so these little guys will all be kind of stuck in here. That's an interstitial alloy. Okay, and interstitial alloys you're also familiar with. If you have stainless steel appliances, okay, steel is one. Steel by itself is usually iron and carbon. When you get into stainless steel, you get the addition of chromium. Cast iron is another one of these. These are alloys. Okay, so remember, the thing with alloys is that they are mixtures, and usually they're designed for a purpose. When you mix them together, you blend the properties. Okay, you want that iron, but you don't want it to rust, so you add that kind of durability of carbon. You want the look of gold, but you want it to be stronger, which is why you add the silver. So this is the end of the ionic unit. Come back for covalence.